Good evening, everyone. Shall we start, sir?
Yes, ma'am.
Yeah. Good evening, everyone. Respected dignitaries. Welcome to Atal Academy FDP on IoT-driven wearable devices for healthcare and defense application. Today, the second day. So it's about mainly Mr. Arun Karthik, sir, is the resource person. The topic is about the nanofibers, applications and technology is the first session. And then the second session is about bioenzyme and then nano-enabled biosensors. So now Mr. Rahul, Assistant Professor, SciTech is going to give the introduction about our resource person. Please, sir.
Yeah, thank you, ma'am. Good evening, everyone. Am I audible? Hello, ma'am.
Yes, sir.
Yeah, okay. Good evening, everyone. It's my immense pleasure to introduce our resource person, Dr. Karthik, Nano Application and Technology, and Bioenzyme and Nano-Enabled Biosensors. Dr. Arun Karthik, working as an associate professor in the Department of Biomedical Engineering at Engineering, Chennai, 9 years in PhD. He completed of degree in Biomedical Engineering from Adiyaman Engineering College, Hosur, in 2009, and Master of Technology in Nanotech from University, Coronal, 2011. He has done his research on NBC filtration and obtained his PhD in Faculty of Technology from Anna University, Chennai. His research interest includes use of nanofiber, nanomaterials, exploration, and biomedical applications and recycling of plastics. He is an active member of professional bodies such as IEEE, IEEE EMBS, IEEE Nanotechnology, of Sensor, Superactivity, and ISTE. He is one of the faculty members of Technologies and Interdisciplinary Research Initiative of SM Engineering. He received many awards in this field and he published nearly 22 journals and he did consultancy and commercialization of 3D printing elements from recycled plastics. Its funding worth to nearly 7 lakhs in Indian rupees. He also developed Feynman Nano Laboratory for research at Chennai. And he visited many foreign countries with full funding support from IIT Madras and also visited Germany. Yeah, once again, I welcome our chief guest, Dr. Arun Karthik, from today's session. Thank you, sir.
Thank you, Rahul. I thank the organizers for inviting me, as well as thanks for the warm introduction. Let me share my slide. Can you all able to see my screen?
Yes.
Yes, sir.
Thank you. Okay, as already introduced, myself, Dr. Arun Karthik, working as Associate Professor and the lab head of Feynman Nano Laboratory at the Department of Biomedical Engineering at Sri Sovasubramanian College of Engineering, Chennai. So coming to the today's topic, the first session, I'm going to talk on nanofibers, its application and technology. So before going to the topic, I'm just going to give you an idea about what is actually SSN. It's a short video, right? Is the video voice is coming?
No, sir.
Okay. Actually, with the NRF ranking 2022, you are ranked 48th in engineering category, and the overall ranking is about 96. Okay, coming to the today's topic, the overview, I'll just give you an introduction about what is actually nanofibers and what are the different techniques that are available to prepare nanofibers, and what makes so unique the electrospinning technique, and some of my works that I carried out using electrospun nanofibers in connection to applications like wound healing, filtration, and protective textiles. Right. So, have we all heard about nanofibers before? Hello. Just to know whether you are aware of nanofibers or not. Can I get a response? Am I audible?
Yeah, sir, we are audible. Yeah, we are aware of nanofibers, but deeply about that. The thing is, we don't know what are the applications that and all. We don't know. We aware.
Okay, thank you. Actually, nanofibers are two-dimensional materials with a fiber diameter less than 100 nanometers. We call it as nanofibers, right? So, especially when we talk about textile industries, those dimension like less than 100 nanometers has been extended till 1000 nanometers. We call it as nanofibers, right? So, this is a typical SIM image where you can clearly see how small these nanofibers are when compared to these polar are uh, the image, the same image as the pollen particles, our human hair, and behind is what we see nanofibers, right? So as you see, when we compare with the size of the human hair and the pollen particles, these nanofibers are so small, right, in connection to diameters, right? So what makes these nanofibers are so unique is its properties, right? So as we talk about the properties, right? So when the fiber size decreases, obviously the porosity increases, and it is going to have high surface area, and we can able to dope more amount of sufficient or the needed nanoparticles to it. As the result, it is going to have high encapsulation efficiency. We can able to play with the size of the nanofibers that we are preparing from 10 to or 100 to 1000 nanometers, right? So and it is going to have high chemical and thermal stability. So when I talk about the chemical and thermal stability, it is going to directly relate to the physical property of the material. That physical property will depends on the type of the material that I'm going to utilize to prepare these nanofibers. So basically, we can prepare nanofibers from natural polymers as well as synthetic polymers. So based on the choice of my material, the physical property is going to vary, right? So there are different techniques that are available to prepare nanofibers. So we have a template method, we have drawing method, we have thermally induced phase separation process, self-assembly, which is going to happen in biological medium, or right. So and the next thing is electrospinning. So each and every techniques have their own advantage and disadvantages, right? I'm not going to explain all these methods. I'm just going to concentrate on electrospinning method because it has been widely used to prepare nanofibers because of its simplicity and easy to fabricate, right? So electrospinning. So the term electrospinning is a technique which is going to produce ultrafine fibers uh, via a charged polymer solution. So we'll be having a syringe pump which is being pumping the polymer solution via a syringe needle, right? Where we will be applying a high voltage electric field, right? So when we apply a high voltage electric field to this solution that is coming out from the syringe pump, right? So when the potential exceeds the surface tension of the polymer, these polymer solution that is coming out from the syringe tip is going converted to fibers, from solution to fibers, right? So this is what it is going to happen, right? So where we have the spinning syringe tip, which is being pumping, the infusion pump is going to pump the polymer solution where we will be applying the high voltage, right? So as the potential exceeds the surface tension of the polymer, right, it's going to form a Taylor cone first, and there is a stable near field. At the far field, these fibers will start whipping. At the collector end, it is being collected as a fiber, right? So this is how we will be seeing those fibers under SEM, scanning electron microscope, right? So this is a typical image of the syringe tip where this polymer solution is coming out on the as we apply the potential, it tends to form the Taylor cone, and there is a transition zone, and at the far field, it starts whipping, right? So this is how the instrumentation will look like, where we have an infusion pump through which the syringe is being connected, which is being pumped at a flow rate, and at the tip, we will be connecting the high voltage. So once the potential that we apply exceeds the surface tension of the polymer solution, the polymer that is coming out from the syringe tip will start whipping. So during the process of transmission, right, from the tip to the collector, the solvent will be evaporate and the polymer fiber is being collected at the collector end. All right. So when we talk about electrospinning setup, we can do electrospinning by two ways. One is by horizontal spinning and one is by this is horizontal spinning and this is vertical spinning, where in vertical spinning we have a more amount of gravitational force acting on the fibers that are coming out, whereas in horizontal spinning the gravitational force will be there, but it will be very less, right? So these are two verticals of electrospinning, and the other parameters is the collector, right? We can use stationary collectors or the drum collectors, right? So that in drum collector, we can able to vary the RPM of the drum collector from say about 100 to 1500 RPM, right? So this image will clearly gives you an idea how these fibers will be change in alignment will be there when we use different types of collectors. So when we use standard collectors, we have misaligned fibers, whereas when we use drum collectors, we will have aligned fibers as well as reduced the fiber size will be reduced when we go with rotating drum collectors, right? So this is the electrospinning setup that we have in our Feynman lab, where we can do horizontal spinning as well as vertical spinning. As you can see, there are two syringe pumps so that we can able to do core shell spinning as well, right? Where we have a core as a one polymer and a shell as another polymer, right? Or else we can able to prepare hollow fibers using this instrument. So this is a video which will clearly gives you an idea about what we are talking till now, right? Sorry. So as you can clearly see, this is the syringe tip. The high voltage has been collected to the tip, where the polymer solution that is coming out from the syringe tip will tends to form a Taylor cone. This is the near field area. At the far field, where you can clearly see the polymer will start whipping, and this is a fog-like structure where n number of fibers are being arriving or coming up from this single point, right? And it is being collected over the collector end. So during the transmission from the tip to the collector, these fibers that are the solvent that is present in these polymers will evaporate, and it is being collected in the collector end. So now you will get a question that how these nanofiber sizes can be varied, because based on the application, we need different specific size of fibers, right? So basically, we have two process parameters that we can play with in order to govern the size of the fibers that we are preparing. One is the polymer solution property and the processing condition, right? So am I going speed, or is it okay?
Is it okay, sir? Not an issue
Okay.
for us.
Okay. So there are these are the two process parameters that we can able to play with in order to prepare nanofibers of our desired size, right? So the one is the solution parameter, and the second thing is processing condition, right? So in solution parameters, right? So solution parameter means the polymer solution that we are preparing, right? So we can play with the viscosity of the solution. We can able to play with the molecular weight of the polymer that we are going to utilize, as well as the solution conductivity, surface tension, the dielectric effect of the solvent that we are utilizing to dissolve the polymer, right? So by playing with this solution parameters, we can able to control the size of the polymer that we need to prepare based on our application. And the next thing is processing condition, which is the instrumentation part, where we can able to play with, the applied potential that is between the tip to the collector and the flow rate that we are pumping the solution through the syringe pump, and the temperature in which the temperature and the humidity in which the electrospinning setup is going to be maintained, and the type of the collector that we are going to use. Either it can be a stationary collector or a drum collector, right? So by playing with these two process parameters, we can able to play with the fiber size that we actually needed, right? Basically it's a trial and error process. We have to play with these parameters and do the SEM analysis in order to identify for this parameter, this is the fiber size that we are obtaining. So by playing with these parameters, we should prepare nanofibers of specific diameter based on our need, right? So there are so electrospinning, we also call it as needle spinning, since we utilize a needle, right? So the drawback with this electrospinning process is the production rate. So the production rate is very less. So in order to overcome the disadvantage, they have used multi-syringe setup or multi-needle setup, right? Even though we utilize multi-needle or multi-syringe setup, the production rate as well as the instrumentation and the power supply that is required, all these makes this electrospinning technique is still it's in a scalable part. It is still a difficult task. Like, so in order to overcome this electrospinning technique, researchers have identified a method called Nano Spider, where the needle is being replaced with wires and cylinders. All right. So same principle where we are going to apply a potential to the needle, right? So when the surface tension is being exceeded by the applied potential, the polymer solution is being converted to fibers. Here also the same principle, right? So this is with where, sorry. Yes. Okay. So where in this video, you can clearly see we have a wire. So this is a polymer reservoir which is moving 2 and 4, right? As it moves, from the polymer will be transferred from the reservoir to this wire. So between the wire and the collector, the potential is being applied, right? So as the polymer, the applied potential exceeds the surface tension of the polymer that is being transferred from the reservoir to this wire has been converted to fibers, right? You can clearly see the conversion of fibers here. So this is with respect to wires. This is with respect to cylinder, where we have a cylinder that is round, rotating. So under which we have a polymer reservoir. As it rotates, it collects the polymer from the reservoir. Similarly, we'll be applying a potential to this reservoir, and the collector will be grounded. As the result, we will be tend to form fibers. So here the production rate is comparatively higher when compared to the needle spinning process, right? So on the next, we have also mill blown process. Where the polymer is being melted and blown with an pressurized inert gas. So this is the spinneret through which the polymer solution is being blown. And it is being finally bound as a fabric, right? So till now we have seen what is actually nanofibers and what are the different techniques that are available to prepare nanofibers, and we have seen especially what is actually electrospinning and what is the principle that is behind electrospinning technique, right? And what are the different ways by which we do electrospinning, and what are the different collectors that are available and the effect of collector, right? So when we talk about applications of nanofibers, it is numerous, right? As you can see from this PPT, that electrospun nanofibers can be utilized in filtration, wound healing, affinity membrane, protective clothing, in energy application, enzyme manipulation, drug delivery, tissue engineering, and various biomedical applications, right? So in the upcoming slides, I'm going to say about some of my works that I carried out by utilizing these nanofibers in connection to wound healing, filtration, as well as protective textiles, right? So the first one is wound healing application, where I have utilized this SPI, which stands for soya protein isolate. It's an extract that is being taken from soya bean that we utilize in our cooking purpose. And PEO stands for polyethylene oxide blended electrospun matrix for wound healing. So when we know about any wound healing process, we whenever there is a sudden accident that happens or a sudden wound that happens in our body due to accident, right, we'll go with wound dressings. So when we talk about conventional wound dressings, we'll use gauges and the cotton. So whenever there is a wound that happens in our body, we will first do antiseptic cleaning in order to remove all the foreign bodies that is present in the wound. Then we will take the cotton swab, take some medicine, put it in the wounded area, and we will tie using the gauge, right? So when we use traditional wound dressing material, it doesn't provide optimum wound healing conditions like hemostasis, non-adherence, as well as maintenance of moist wound bed. So researchers have identified when we use specific amino acids, which helps in the healing process. So researchers suggested that arginine and glutamine will be useful for wound healing. Why arginine and glutamine is? Arginine is efficient in wound repair and immune function, whereas glutamine is utilized by the inflammatory cells in the wound for proliferation and act as well as a source of energy, right? So when we search in the literature, we found the soya protein isolate, that is the extract that is obtained from soya bean is rich in arginine and glutamine. We thought of utilizing these property as a wound dressing material, right? So we started electrospinning soya protein isolate. What we observed is we can't able to convert these polymer into fibers because of its globular structure. Like it is not getting converted to fibers. So it's just whenever we done electrospinning with SPA, it's just splitting the polymers. Like we are just getting a beads. So because of its globular nature. So we blended, that is the reason we blended it with dissolving oxide to convert into a fiber. So here PEO is a fiber forming agent, right? So what we actually did is we taken 10% PEI, soya protein isolate in 1% NaOH, and 4% of PEO was dissolved in ethanol. So, and we blended this solution in the ratio 20-80, 40-60, and 60-40. So when we do when we done electrospinning for these ratio, 60-40 doesn't give us nanofibers because of its higher proportion of soya protein isolate. Only 20-80 and 40-60 gave us nanofibers, right? So and we so out of these two samples, we took 40-60 for the further studies because 40% of soya protein is comparatively higher than 20%, is going to give us a better yielding than 20%. So we took 40-60 and then electrospinning. So this is a SEM image of the prepared nanofibers. This is the pure PEO, right? So this is with stationary collector. This is with drum collector. As you can clearly see, the fibers are the fiber roughness is quite high in case of stationary collector than drum collector. Here it is smooth surface. Here it has rough surface, which you can clearly see the twist and turns. So as you, when we biologically have an advantage of this rough surface because cell will adhere more to the rough surface than smooth surface. So we took these samples for further analysis. So the electrospinning process parameters that we utilize to prepare these nanofibers are, we use a syringe needle size of 18 gauge and the applied voltage is 15 kV and the flow rate is about 1 ml per hour. And the distance between the tip to collector is 15 centimeter. Later on, we characterized these prepared nanofibers under FTAR in order to know the functional bands that are available in the prepared sample, because we are subjecting these polymers at high voltage. Like these biopolymers may denature when we apply high potential. Like the results shows the functional groups are still present in these prepared nanofibers, where the NH, the amine groups is obtained at 304 to 3250 in all the peaks of SPA and SPA PEO. And CH alkene peaks of PEO is observed at 3000 to 2850 in both PEO and SPA PEO. And the carboxyl group is between 1760 to 1690. Which clearly confirms the functional groups or the functional aspects of the biopolymer is not being affected during the electrospinning process when we apply electrical potential. So then we studied the moisture vapor transmission rate, which is an important parameter for a wound healing material, right? So, this moisture vapor transmission rate plays a major role in the healing process of a wound. Right, so it all depends on the type of wound. Whenever the wound is small, we don't cover those wounds, right? So whenever there is a severe tissue loss, then only we'll go ahead with wound dressing materials, where this moisture vapor transmission rate is going to maintain the adequate level of moisture in the wounded area, right? As everyone can observe, whenever there is a wound exudates that is going to come out for a few days from the wounded area, right? So this wound exudate has to be removed from that area, as well as a proper moisture environment has to be maintained in the wound area in order to heal faster, right? So the recommended rate for wound healing is about 2000 to 3000 grams per meter square per day, right? That is adequate level of moisture vapor transmission for a wound dressing material in order to maintain proper hydration in that area, so that dehydration will be avoided. So if the area is complete is hydrating more, then the healing will happen at a slower rate, as well as the risk of infection by microorganism will be higher, right? So from the table, you can clearly observe that this is the sample with between PEO and SPA PEO, where you can clearly see the blending of SPA with PEO was in the recommended rate, right? So the moisture vapor transmission rate is 2,994 grams per meter square per day, right? So, and we tested the mechanical properties of the prepared material, where, as I already mentioned, this SPO is a globular protein, right? So as I blend with PEO, the tensile strength of the material increased from 1.2 megapascal to 2.3 megapascal, and the elongation decreases from 17% to 9%. And as arginine and glutamine have good antibacterial activity, so the zone of incubation was also seen when we test the antibacterial activity against both gram-positive and gram-negative bacteria. So, and further we tested against the female Wister rats by creating a wound in the rat. The two wounds of similar size has been created, and one wound has been left as such to heal, and the other wound has been dressed with the dressing material, the nanofibrous material that we prepared. As you can clearly see from the day 2, day 4, and day 8, the wound healing was much faster in the nanofibrous dressed material compared to the open wound. So as you can clearly see in the 8th day, the wound has been completely covered, and we can clearly see the hair starts growing, right? So from this investigation, we conclude that SPA-PEO was successfully prepared as a nanofibrous matrix, and the prepared nanofibers showed good antibacterial activity against both gram-positive and gram-negative bacteria. And when the in vivo studies of the prepared dressing showed good results, or increased rate of wound healing compared to a non-dressed wound, and there is no adverse effect as well. So which shows this can be utilized as an ideal wound healing material. So, and the next one is in connection to filtration application, right? So I'll just give you an idea of why we go with filtration application. So as you all know, we'll be utilizing our daily dresses which are being dyed using dyes, right? So the dress looks with different colors due to dyes, right? So these dyes, there are different sort of dyes: reactive dye, non-reactive dye, acid dye, right? So these dyes are toxic to the water bodies as well as to the humans, right? So as per the government law, the dyes that are being utilized in the textile industries are to be treated or degraded by using photocatalytic materials, right? So the commercially used photocatalytic material is titanium dioxide, right? Titanium dioxide is the commercially used photocatalytic material, right? So the problem with titanium dioxide is they are activated in the UV region, right? So visible light activation is not possible in titanium dioxide. What we done in this work is, and another disadvantage is, so whenever the textile industry utilize these photocatalysts, recovery of these photocatalysts after the photocatalytic activity is quite difficult, because they are putting these powders in the direct dye solution, which will degrade, and again they are utilizing these water, or again they are degrading or putting these waters in the water bodies. Again, these TiO2 again is going to contaminate or cause pollutants, right? So in order to avoid that, we have prepared a membrane-like structure utilizing nanofibers, in which we have doped these TiO2, and we tried converting these TiO2 nanoparticles as a visible photocatalyst by doping lycopene. The motto, right? So to give you an idea, lycopene is an unsaturated hydrocarbon containing 13 carbon-carbon double bonds. So which is the reason for the red color in the fruit tomato and watermelon, right? So why we choose lycopene is because it absorbs visible light. So as we are doping lycopene with TiO2, it is going to activate TiO2 as a visible light photocatalyst, so that the problem can be overcome. And it acts as an electron donor, which again helps in the degradation photocatalytic process. And these lycopene acid is going to be extracted from natural source like tomato and watermelon. It is a non-toxic material. So what we actually done is, we have taken tomato, we have crushed it, and we have filtered, and the filter cake again mixed with CCl4, and it is allowed to phase separate. And the separated red color solution is again taken back and we done column chromatography and we have extracted the lycopene finally. So this is how we have extracted lycopene, and the extracted lycopene was characterized. So the peak at 443 and 470 and 501 gives the confirmation that the extracted medium was lycopene, and this is the optical microscope image of the purified lycopene. As you can see, it's completely red in color. So then we utilize lycopene as a reducing agent to prepare a TiO2 nanoparticle complex. For titania, we have taken titanium tetrabutyl as the source, and we mixed with the lycopene extract, and we further centrifuged and dried in auto oven and kept it furnace for 450 degrees Celsius, which results in lycopene TiO2 nanoparticle complex. So again, these nanoparticles, as I already mentioned, these nanoparticles are the photocatalysts are being mixed with the dye solution. Once the photocatalytic activity has been completed, so the water with these photocatalysts are being discarded into water bodies, right? So that the possibility of recovering those photocatalysts from the water is a difficult task. So we have prepared a membrane as a photocatalytic membrane. So for preparing a membrane, we utilize the electrospinning. Now, electrospun nanofibers which has been prepared from polyalkyl nitrile. So why we choose polyalkyl nitrile? Because of its we can able to easily produce nanofibers. It is hydrophobic in nature and they are chemically and thermally stable. So we have now lycopene incorporated TiO2 pan, and we have prepared 9 membranes out of it, 9 photocatalytic membranes with different concentrations of with different dopings of TiO2. That is 20, 30, and 40, and we varied the electrospinning time 3 hours, 5 hours, and 6 hours. So this is the electrospin parameters that we utilized. So totally 9 samples have been prepared. We named it E1 to E9. So we characterize the fiber diameter. So for 20% loaded nanofibers, the average fiber diameter is is about 359 nanometers. So and the distribution of the fibers is between 350 to 400 nanometers. All right. Whereas 30% incorporated nanofibers, average fiber size is about 190 nanometer, and the range of distribution is between 180 to 200. For 30% LTC, the is about 338, and the range is between 320 to 480. So from this semi-image, we observed as the percentage of LTC increases from 20 to 30, the fiber diameter decreases from 360 to 190 nanometer because of the increase in the conductivity of the solution due to increase in the TiO2. But when we increase from 30 to 40, again the fiber diameter increases. This is due to the aggregation or the agglomeration of these nanoparticles that we added, right? Later on, we studied the FTR spectra of the prepared nanofibers. So 2243 gives us the nitrile group C triple bond N functional group, and the peak at 872 gives CH stretching of lycopene, and 2930, 2870, and 1460, 1450, and 1380, 1360, and 1363 corresponds to CH2 group of lycopene and pan, and 2938 and 2869 and 1449 corresponds to CH group of lycopene and pan. CO stretching is seen at 1072, and TiOC stretch is seen at 1044, and TiO stretch is seen at 535. So, and later on, we checked the prepared membranes, porosity, and water uptake. So this is an important parameter for any membrane when we go with water-based application. So porosity will directly give us the water permeation through the membrane, and the water uptake. So as you can clearly see, in all these samples, this is 20% incorporated, this is 30% incorporated, this is 40% incorporated, right? So with the different electrospinning time, as you can clearly see, 30% incorporated sample gave us higher porosity and higher water uptake, because the fiber size is quite less in case of 30% incorporated LTC. As the fiber size decreases, the porosity increases, and the surface surface to volume area also increases. That is the reason for higher amount of water uptake, right? So with increasing time duration, it decreases, right? Later on, we checked the different process parameters of the prepared nanofibers, like the GSM, the thickness, the water uptake, and porosity of all the membranes. As you can clearly see, with increasing time, the thickness of the material increases, and as the fiber size is quite less in case of 30% LTC, incorporated LTC, in all the samples, there is a decrease and increase, because 30% incorporated fibers are less in diameter. As a result, the packing density is quite high. As a result, the thickness is less in case of 30% LTC. Later on, we checked the pure water flux, the protein flux, and the pure water flux after washing. So this is an important parameter which is used to measure the choking of the prepared membrane. So where the 30% LTC incorporated membranes gave us good results in all the cases. And we checked the anti-fouling property of the prepared membrane. 30% samples gave good results. Among the 30% LTC samples, E8 membrane showed a higher flux recovery ratio. As you can clearly see, E8 membrane showed a higher flux recovery ratio. This is the drop. So this is the initial pure water flux. After blockage with the protein, it has been dropped to here. So after washing the protein, again it has been recovered higher, quite similar to that. So in other cases, the recovery is quite less. And then we checked the adsorption of dye over the membrane. Later on, we checked the ultrafiltration property of the membrane using an oil-water separation technique, where we found out E1 was the highest in case of permeate flux, and E8 was less. Since the fiber size is less and the packing density is more, E8 membrane showed lesser permeate flux, but in contradictory, they have 77% of oil water separation, whereas E1 showed 51% of filtration efficiency in case of ultrafiltration testing. So this is the setup that we utilize to check the dye degradation efficiency, where we have taken the dye solution, that Congo Red, as a dye solution for our work. This is a feed tank in which we have taken the dye solution. This is the visible light, the meter which is used to measure the lux value that is coming out from this LED. And this is the photocatalytic membrane where we placed, and the dye solution passes through this membrane. So these photocatalysts that is present in this membrane are being activated by this light that is coming out from the LED. So and it is going to react with the dye solution, and the dyes are going to be degraded, right? So this is the dye degradation efficiency of the prepared all 9 membranes, in which the sample E9 gave us highest degradation efficiency of 60%, right? This is the, and we have calculated the rate constant R square. As you can see, the R square are quite similar or near to 1, which significantly says this is a first order kinetic. So what is the first order kinetic reaction which we done? So in order to identify what is the degraded product of the dye, we took GCMS of the samples. So we found the byproducts as biphenyl. The Congo Red has been converted to biphenyl, naphthalene, and phenol. So this is the corresponding GCMS spectra. So from this GCMS result, we derived this equation. Like the Congo Red is being cleaved. We get a cleaved azo dye. Right? These cleaved biphenyl diamine is being on deamination gives biphenyl, and these amine group on deamination and desulfonation gives naphthalene, and which is again hydrolyzed, which undergoes hydrolysis and dehydrogenation gives phenol. That is why we got biphenyl, naphthalene, and phenol as the byproduct in this case. So then in order to identify which membrane is number 1 in ranking, we framed a equation for identifying as a quality factor, in which we have given weightages to different parameters that we measured. So the weightage that we given is flux recovery ratio, permeate flux, solute rejection, and dye degradation. Based on the results, quality factor, it has been identified E8 membrane that was made using 5 hours of electrospinning with 30% of LTC gave us number 1 rank in connection to with respect to the quality factor value. So from this result, we conclude that lycopene TO2 nanoparticles was successfully prepared by incorporating in pan nanofibers as a photocatalytic membrane, and 30% LTC gave us better results compared to 20 and 40, right? So in connection to anti-fouling property, BSA, the bovine serum albumin that we utilized as a protein coagulant for measuring the choking of the fibers, gave us lesser choking in 30% LTC because these are being uniformly distributed, and it avoids these clogging of proteins in the fibers. And we have achieved a dye degradation of about 60%, and the flux recovery ratio is about 68%. And the degraded products were biphenyl, naphthalene, and phenol. All right. So based on the quality factor results, E8 membrane is the best membrane out of all 5 membranes that we prepared. So, and finally, we are suggesting E8 membrane can be utilized as a catalytic membrane for dye degradation. As I already mentioned in the starting, right, there are 2 drawbacks that are available. So, whatever the photocatalytic membrane, photocatalysts that are used in the dye industry are being discarded after degradation in the water bodies, right? So, as we incorporate these photocatalysts in the membrane, we can recover those photocatalysts back for utilization, right? So that can be overcome, and we have an efficient filtration efficiency. As the fiber size are lesser, we have higher amount of encapsulation efficiency, right? So on the next, and the other drawback that we found in the past study is these nanofibers are quite fragile in nature. So the handleability is quite difficult task. So the mechanics, what I mean is mechanical strength. So in order to improve the mechanical strength as well as the functional aspects of the membrane, we further done a research on preparing triple layer membrane, where we utilized 3 layers, right? We have intermediate layer, which is made of nanofibers, and the top and bottom layer is made by polymer solution by phase inversion technique. So this is the intermediate layer. This is the top and bottom layer that we done using phase inversion. So where we maintained the electrospun layer as a constant, and we checked vary the top layer proportion with nylon and PEG. So as you all know, nylon is hydrophobic polymer, which doesn't allow to water to pass through it. So mostly nylon fabrics are being utilized in raincoats like that. So in order to increase the porosity, we are mixing the PEG, the polyethylene glycol, which is a pore former, right? We are blending this and preparing the top layer and bottom layer. So this is a typical same image of the 3 membranes that we prepared. So this is the top layer, and this is the intermediate, and the pores that is corresponding to the layer. Right, as you can clearly see, as the PEG, pore forming agent, continuously increases, the exposure of the intermediate layer is going to increase. It is getting increased, right? So, and we checked the parameters like mean flow pore diameter, bubble point diameter, and the smallest pore size and the largest pore size in all 3 samples. As you clearly see, nylon with lesser, the TLM1, the triple layer membrane 1, has higher pore size and a higher mean pore diameter. Even though it has bigger pore size, the pores are uniformly distributed, right? Whereas in other TLM2 and TLM3, because of increasing pore former, there are irregular distribution of pore size is being clearly seen. Then we checked the XRD of the prepared membranes, where the peak at 1413 and 1313 and 1213 correspond to the pan, and 20 and 23. This 20 and 24 and 20 and 24, 2 theta correspond to the nylon. Then we study the thermal gravity of the prepared layer membranes. So for pure pan, the degradation starts at 330 degrees Celsius, whereas when we incorporate or when we blend nylon and pan, the degradation temperature increases further from 330 to 364 and 362 and 350. The decrease in degradation temperature is due to a decrease in the content of nylon, right? Then we check the pure water flux and filtration efficiency. As you can clearly see, the pure water flux was quite less for TL1 because of its lesser amount of pore former agent, but the filtration efficiency is higher, right? Which is the case in other two. Where in TLM3, we have higher pore former agent so that the pure water flux is higher, the water that is passing through the membrane is higher, and the filtration efficiency is lesser. So based on the results, we found the filtration efficiency for TLM 1, 2, and 3 are 96, 87, and 41. So from the results, we found TLM1 to be a suitable candidate for filtration application. With this study, we prepared a triple layer membrane which has more functional property than the earlier previous study, with improved functionality as well as improved strength. Right. So and we also found the effect of pore former, right, has to be chosen in a statistical manner so that we can able to produce a uniformly distributed pores, which is going to give us better functional property. So optimizing the concentration of pore former, as I already mentioned, is an important thing which we should consider in preparing this triple layer membrane, which is going to act as a promising membrane technique in order to remove organic pollutants from the water. And the next one is multifunctional nanocomposite nanofibrous membrane, which is going to relate with the protective textiles or the protective defense application, right? So which is our patented work, and the patent has been granted with the patent number 354229. And we also published the same work in chemical engineering communication, right? So as we all know, health threats, right, due to air pollution is a serious concern, right? So when I talk about health threats due to air pollution, it is basically from particulate matters, biological agents, and chemical agents. So when we specify particulate matters, it is PM10, PM2.5, and PM0.1. So out of these PM classification, PM2.5 causes serious health issues like cardiac problem, nausea, other like more sort of problems has been caused by PM2.5. Besides TPM2.5, we also have biological warfare agents, right, and the chemical warfare agents. So chemical warfare agent includes nerve gas, mustard gas, right? So all these are obviously on inhalation by the human being is going to cause serious health hazards. Whereas these biological warfare agents and chemical warfare agents leads to sudden death, right? So that is which clearly gives us military as well as general public needs high level of protection whenever there is an accidental or intentional release of these agents in the atmosphere, right? So in order to protect mankind from these agents, electrospin nanofibers can be utilized as a protective filters, right? So basically from this slide, you can clearly see a full face respirator. So this has been widely used by the military people during emergency release of these chemical agents and biological agents in the environment. What are the difficulties are, or they are uncomfortable when worn for a long period of time, right? So they are made of fabrics, the diameter in the range of microns, so that they are poor in biological and chemical filtration. And these cartridge filters are separately prepared. So if you want chemical filtration, you need to purchase a separate cartridge. If you want biological filtration, you should purchase a separate cartridge, right? So there is no multi-purpose mask which will filter all three of these agents in a single cartridge. And even though you buy different cartridges, these cartridges will only filter those agents, doesn't detoxify, right? And when we go with cartridge type filters, they are huge in weight, right? So all these are a problem with current respirators, right? So we thought of developing a single filter which is going to act again all these agents. Like it's going to filter PM 2.5, it is going to filter biological agents as well as chemical agents. Also, it is going to act against these biological agents and chemical agents, right? So that is what the aim of the work. So we prepared a triple layer membrane. This is the exploded view of the filter that we developed, right? So where we have the inner surface and the outer surface made of PP spun bonded non-oven, all right? And the middle, between the spun bonded non-oven, we have incorporated 2 layers of nanofibers. So the first layer is made of polyacrylonitrile with silver incorporated membrane, and the second one is made of polyacrylonitrile with magnesium aluminate. So this is the same image of the prepared 2 layers. So magnesium aluminate have a fiber diameter of 211 and the silver nanoparticle has a fiber diameter of 123. And we checked the degradation of the chemical agent. So we can't use chemical agent directly because of clinical issues. So we chosen simulant 2CS, that is 2-chloroethyl ethyl sulfate, right? So which is a simulant for sulfur mustard, right? Where 250 ppm, 250 ppm is the LD50 value, right? We have taken 500 ppm and tested its degradation efficiency with the prepared membrane. As you can clearly see, 95% of the 2CES that we take and that 500 ppm is being degraded, right? So when we have studied the rate constant and half-life by studying the kinetics, the rate constant is about 0.019 minutes and the half-life is about 36 minutes. And we have studied the degradation product. So the 2CS has been converted to something, right? So that degraded product has been analyzed by GCMS. What we found is the degradation product is vinyl ethyl sulfide, chelated hydroxyethyl ethyl sulfide, chloroethyl ethyl sulfoxide, and vinyl ethyl sulfoxide. These are not as much toxic as 2CS, right? So from the products, we identify the scheme of degradation that 2CS on interaction with magnesium aluminate. On oxidation, it forms chloroethyl ethyl sulfoxide. On hydrolysis, it gives chelated hydroxyethyl ethyl sulfide. On elimination, it gives vinyl ethyl sulfide. On oxidation and elimination, it gave us vinyl ethyl sulfoxide. Then we checked the filtration efficiency against bacteria and aerosol. As you can clearly see, the aerosols, the overall filtration efficiency is about 99.54. As you can clearly see from the image, the aerosols, the PM 2.5 that entered through this membrane are being trapped between the fibers, right? So, and we checked the filtration thickness, mean flow pore size, and the air permeability was quite high compared to the cartridge filters. And the pressure drop was minimum like 6.5 mm in water. And the bacterial filtration efficiency was about 99%. And we checked as I already mentioned, it is not going to filter, it is also going to act against the biological agent and chemical agent. So the chemical agents are being filtered and degraded to 95%, whereas in bacterial agents, we tested against both gram-positive and gram-negative bacteria. As you can clearly see, 81% of the gram-positive is killed, and 67% of the gram-negative bacteria is being killed in connection to viable study. So with this, we found we have developed a multifunctional filter, which is being utilized for military purpose, as well as a common person can be utilizing these filter to protect against these ABC agents, right? So, and we found out 2CS was being degraded by hydrolysis, elimination, and oxidation. The prepared filter gave us 99% filtration efficiency against both bacterial agent as well as aerosol agent. And to conclude, so it is a simpler technique. By utilizing a simpler process, we have prepared an multifunctional filter, which is going to act against all these agents, 3 agents, that is aerosol, bacterial, and chemical agents, right? And it is going to detoxify these agents, right? And more importantly, these are lightweight filters, right? As you can clearly see, the thickness right? It's only 0.831 mm, right? So the GSM is around only 40 GSM. So it's less than an A4 sheet paper, right? So this is the end of my session 1. So we will discuss the question and session. So we'll discuss if you have any doubts between 9 to 9:30. Is that fine, madam?
Okay, sir. In discussion forum, we will discuss the doubts of the participants.
Okay. Okay, now the time is 8. Shall we join by 8 in, ma'am?
Oh, okay. 8 and we will join again.
Okay.
Participants deconnected. Don't leave. After 10 minutes, we come and listen. Thank you.
Dear participants, now the 10 minutes short break. After the break, we will start the session. So please don't leave the link. Be connected with us. Thank you.
Ma'am, shall we start?
Yes, sir.
Shall we start, sir?
Yeah, yes, ma'am. Is my screen visible?
Yes, sir.
Okay. So once again, welcome you all to the second session. I hope all are hungry, right? I'll complete it as soon as possible. So the second session of my talk is on bioenzyme and nano-enabled smart biosensors, right? So the overview will be I'll be just giving you an introduction about what is actually biosensors. Maybe you would have already seen these slides in the first day of your FDP. So the operating principles and what are the different types of biosensors that are available and how these biosensors are being utilized in connection to COVID-19 that we are seeing in the past 2 years. Right? So biosensors. So the concept of biosensor was first addressed by Clark and Linus around 1962. So the figure that you see here is Professor Leland Clark, who is called the father of biosensors. What they actually developed is an oxidized enzyme electrode for glucose reduction. Right. So when we talk about or when we say biosensors, right? So they are a measuring device in which the analyte is going to interact with a biological component, which is going to undergo a physicochemical change, which is being detected, right? That is why we call biosensors as a measuring system. So the biomolecules such as nucleic acid, protein, cells are being detected in these biosensors which are being concerned or associated with disease. Biosensor biologically sensitive to detect the three reader device, right? So enzymes, microorganisms, organelles, antibodies, nucleic acids, all these or can be utilized as or being used to detect biomolecules, right? So there is one more component called high quality biosensors, which are nothing but fully functional device, right? So when we say biosensor, it should be a fully functional device. Then only we say it as high quality biosensors. So in order to develop a high quality biosensor, we should choose proper material, proper transducing device, proper biological element. So before going to an assembly, we should be clear with all these materials in order to develop a fully functional device, which we call it as high quality biosensor, right? So as I already mentioned, there are three components in biosensor, right? One is a biologically sensitive element, and the next thing is detector element and reader device. So biologically sensitive element, we also call it as bioreceptors, right? Where the biologically sensitive element can be cells or microbes or cell receptors, antibodies, enzymes, nucleic acid. All these can be utilized as a biologically sensing element, right? So these biologically sensing element is going to interact with the analyte of our need, and these analyte and the sensing element is going to undergo a physiochemical change, right, which is being identified by the transducer, right? So based on the transduction technique, right, we will be classifying these biosensors into optical, electrochemical, and piezoelectric biosensors, right? So the next thing is transducer. So transducer is a sensing device or a sensing component in the biosensor, which is going to determine the physiochemical change that happens during the analyte and biosensitive element interaction. Right, that physiochemical change is being identified and being converted into a signal which can be evaluated and quantified. And the next thing is the next component is a reader device, which can be a software or an hardware, which is going to display the results that is being produced by the transducer. Right, so it's like a user interface through which we are going to interact with the biosensor. So this is a typical block diagram of a biosensor where we have a biologically sensing element, biological sensing element, which is going to interact with the analyte of our need. So on these interaction, it is going to undergo a physicochemical change, which is being identified by the transducer, which is going to give us a produce a signal which are being evaluated and quantified. And these signals are being processed and given or shown by the reader to the user. All right. Can anyone give an example, a practical example that you come across that we utilize in our day-to-day life? Anyone example? Any biosensors that we utilize in our day-to-day life? No reply? It can.
Thermometer is a biosensor, and the pregnancy tester is a biosensor.
Yeah, pregnancy test kit is the good example for a biosensor. So, thank you, ma'am. Yeah, COVID testing.
Also,
So the RT lamp, which is similar to pregnancy test kit that was introduced in the first wave, I think for faster detection, that RT lamp test is also an example of biosensor, right? So the generally we use pregnancy test kits, right? So it's an example of commercially and widely used biosensor, right? So what is actually there in the pregnancy test kit is, so the pregnancy test kit is used to detect a hormone called HCG, that is human chronic gonadotrophin hormone, which is usually high in case of early stages of pregnancy, which comes out in the urine. So whenever a woman is pregnant, so they will be having higher amount of HCG in the early days of pregnancy, which comes out in the urine. So the specific antibodies against the HCG is being doped in the pregnancy test kit. So whenever the sample pad is being put with the urine samples of the woman, so whenever the HCG present in the urine sample, the antibodies and the HCG will interact, will tends to change the color. Okay, so this is how we will have our results. If there is a two, it is positive. If it is one, if there is no color change in color, then it is negative, right? So it's a simple biosensor that we are utilizing. Any other example other than COVID test kit? Okay, so our day-to-day life, the glucose monitoring device is also a biosensor, right? So where you will take a drop of a blood by pricking, and it is placed in a strip where we have an enzyme electrode. So that strip is an enzyme electrode. The enzyme will react with the glucose in the blood and will generate a current flow. So the amount of glucose that is present is directly going to relate to the current that is being generated. So that current is being converted into appropriate glucose reading. So this is how we generally know how glucometer or a glucose meter will work on. Like the basic thing that goes behind that is there is an enzyme called glucose oxidase. Okay, in the enzyme strip, we have an enzyme called glucose oxidase, so which is going to interact with the glucose that is present in the blood, and these glucose oxidase is again on interaction with the glucose will be converted into gluconic acid, right? Again, this gluconic acid is going to interact with one more chemical component, that is ferric cyanide in this strip. So upon gluconic acid, upon interaction with ferric cyanide, will convert into ferrocyanide, which liberates or generates current, right? So for each and every single glucose, there will be conversion of ferrocyanide, ferric chloride to ferrocyanide, which liberates the current, by which we can directly relate the amount of glucose that is present in the blood. This is the basic principle that works behind the glucose monitoring device, right? So when we come to the performance of biosensors, right? Now to analyze the performance of the biosensors, we have 5 important parameters, right? One is selectivity, reproducibility, stability, sensitivity, and linearity. What actually selectivity is? The capacity of a biosensor to detect the specific analyte in an n number of analytes. So for example, if we are going to analyze a blood sample, it is going, for example, if we are going to detect, if we want to detect RBC, like apart from RBC, we have WBC, the n number of components in the blood cells, right? So sensor need to be so specific so that it will interact with the analyte, specific analyte of our need, right? And the reproducibility, able to produce same response with multiple times of repeating the same procedure, right? So reproducibility will give us the reliability and robustness of our biosensor what we developed, right? And the next thing is stability. Here the stability doesn't mean about the results that we get with multiple times. It is about the endurance of the biosensors with respect to the ambient disturbance. So the biosensor in capacity to omit the surrounding environment changes, right? That is what we mean stability here. And the next thing is sensitivity. Sensitivity is the limit of deduction, the LOD that is needed, the minimum amount of analyte that a biosensor can detect will give us the sensitivity of the biosensor. And next thing is linearity. Linearity examines how accurately the biosensor will determine the change in the analyte, right? So, for example, if the analyte range of concentration is if we vary the analyte concentration, a small variation, right? Whether the biosensor can able to predict those small variation in the change, that gives us the linearity of the biosensors, which gives us the resolution, right? The resolution of the biosensor that we developed. So based on the transduction technique, these biosensors are classified, as already mentioned, optical biosensors, electrochemical biosensors, and piezoelectric biosensors. So when we talk about optical biosensors, so as the name itself clearly says, it's the measure of photons, right? Using optic fibers as transducing elements. So here, the mechanism that is employed for optical biosensors are absorption, colorimetry, fluorescence, and luminescence. The advantages with optical biosensors are low noise, and there is no electromagnetic interference that happens. The next thing is electrochemical biosensor, which is widely used for pathogen detection, where the analyte is going to interact with the electrode, right? So where the interaction of the analyte and the electrode is going to be converted as a measuring electrical signals. What actually happens is the analyte is going to result interaction of this analyte with the electrode is going to create a redox reaction between the analyte and the biological element, which is going to create a catalytic reaction, right? So as the result, there will be capture of electrons, which we measure under a current, right? So here we utilize potentiometry, amperometry, or conductometry as the measurement technique, right? So these electrochemical sensors are improved a lot. The field of electrochemical sensors has improved a lot by the advancements in bio-nanomaterials, with the development of bio-nanomaterials. Next is biosensors. As you all know, piezoelectric material are the material able to generate voltage under mechanical stress? Similarly, when we apply a electric field, it will oscillate at a frequency, like at a resonant frequency. Right, the working principle of piezoelectric biosensor is quite easy, right? So as we apply a potential or electric field, it is going to oscillate at a certain frequency, right? When these piezoelectric materials are being capped with or functionalized with a biologically sensitive element, right? So these sensitive element or upon interaction with the unlight, the mass of the piezoelectric material will varies. As the result, the resonant frequency will change, right? So the change in resonant frequency is being utilized as a mechanism to measure the analyte of our need in piezoelectric biosensors, right? So when we talk about biosensor market in US, as you can clearly see from the graph, the CAGR of biosensor market in US is growing at a rate of 8.84 with a budget of 27.6 billion USD in the year 2022, right? So when we know the when we study about the global market, global market, sorry, the CAGR was about 8%, right? And the market share has been increasing year by year, and most of us will be using wearable biosensors, right? Wearable biosensors are growing at a CAGR of 9.3. I think most of us are being utilizing with wearables like Fitbit, any sort of now the watches are being replaced with wearables where we can able to measure SpO2, sleep tracking, walking parameters, exercise parameters. All these parameters are being measured with a wearable smartwatch, right? Which clearly shows us the biosensors market is being increasing year by year. So the current CAGR of global market is about 8%. So when we talk about biosensors, right? So even though we talk about biosensors, the utilization of biosensors with respect to applications specific is what been shown in this table. So this is a China biosensor market as per the statistics of 2018. As you can clearly see, most of the biosensors that are developed, the first goes with blood glucose testing, followed by cholesterol testing, and third by blood gas analysis. Fourth only pregnancy testing, and fifth is drug discovery. Sixth is infectious disease testing, right? So this is how the biosensors market is being distributed in China. It will be similar in other countries as well, because we won't go. Still, the technology is not up to the level of other areas of testing, right? So I'll just give you some of the simple biosensors that are being developed with respect to each and every technique. One with optical sensors, one with electrochemical, and one with piezoelectric biosensors, right? So Vidal and their team has developed an visible optical biosensors with the use of nanofibers, right? In the previous session, we have seen nanofibers and its application, right? So similarly, these nanofibers are being utilized as a visual optical biosensor. It's a simple technique that they utilize, right? As you all know, skin burn injuries, right? Skin burns are the major cause of death worldwide. Like 180,000 deaths per year is been occurring due to skin burns. So the death that happens due to skin burns are not due it's not actually due to the burn or the wound that happened in the person. So it is actually the pathogen infection that happens after the skin burns, right? So early detection of the microorganism that enters the site is one way by which we can able to prevent or isolate the person from that environment, so that there won't be further pathogen infection or microbiology infection that happens in the skin wound. Okay, so the early detection of pathogenic bacteria in food, water, and public places, including hospital, is a is a need, right? So what they actually found is they have prepared an electrospin nanofibrous matrix using PVB, that is polyvinyl butyryl, and polydiacetylene. Okay, they blended these polymer and prepared it into nanofibers, and they have sterilized those nanofibers under UV. Okay, so and they exposed these nanofibers with both gram-positive and gram-negative bacteria. As you can clearly see, these nanofibers turns pink color when it is being exposed with gram-positive and gram-negative bacteria. This is due to the uh, steric crowding that happens in the surrounding ligaments at the backbones of PD. Okay, due to this, there is a color change, which is the optical color change that happens. As you can clearly, so which gives you a simple optical biosensors, right? So from this, by utilizing these nanofibers, we can simply place those nanofibers in an environment, and we can able to, if there is a change in color, we can clearly say whether this environment has a higher amount of microorganisms or not. So this change in color happens within 30 minutes of exposure. Okay, so now you can realize the advantage of nanofibers in real-time studies, that too without any chemical sophistications. Right, this is a simple. We are going to place the sample in an area where we need to measure. If the color is changed, we can able to identify whether it is whether the environment is microbial free or not, right? So the next thing is VOC deduction, that is volatile organic compounds such as ammonia. Detecting ammonia is a challenging thing, right? So the level of ammonia in the air using gas vapor sensor is of great demand right now. Not only ammonia, all VOC volatile organic compounds are going to cause a serious threats to the mankind, which are to be detected. Right. So biosensors can be utilized to detect these VOCs. Right. Here also they have utilized the electrospun nanofibers. Right. What they actually did is they utilized the principle of piezoelectric material. Right. What they actually taken is they have taken the oscillator frequency of piezoelectric material. Right. These piezoelectric material are being coated with pan nanofibers that is being doped with citric acid. Citric acid has the tendency to interact with ammonia, right? So they have taken a closed container. So here they have taken the piezoelectric material, which is being coated with the nanofibers that is doped with citric acid. So this it is in the closed container is connected with fresh ambient air and ammonia. Okay. So whenever, so as we all know, whenever apply electric field, these photoelectric material, or sorry, the piezoelectric material is going to oscillate at a resonant frequency. Okay. Whenever an ammonia is being injected to the sensing chamber, right? So as the citric acid and the ammonia has a tendency to interact, the resonant frequency changes. Okay. So this is the principle that behind that. So the sensor undergoes a sharp frequency shift and reaches a stable value after several seconds. So whenever we again and pure ambient air has been purged to the sensing chamber, again the frequency, resonance frequency comes back to the normal. So by this way, they can able to clearly detect the presence of volatile organic compounds. Here the case they mentioned is ammonia. Okay. So pan with citric acid can able to detect ammonia vapor of 0.28 ppm parts per billion. Okay, so and they are quite the sensor that they have developed is quite reversible, and they have repeatability and rapid response, and the recovery time is also quite high. Right. So this work gives you an idea about how the quartz crystal microbalance, so our piezoelectric material can be utilized as a biosensors. And the next thing is simple electrochemical sensors. As I already mentioned, electrochemical sensors are being widely used for pathogen detection, right? So pathogen, as I already mentioned in the first slide as well, like pathogen detection is the main reason for death due to skin burns, right? So reduction of pathogen is quite important in case of hospitals, clinical diagnosis, food industry, water, and environmental quality, right? So the traditionally how microbes are identified is they are identified by culturing or by colony counting method, right? So by utilizing nanotechnology and biosensor property, we can able to identify or sense these pathogens in a faster way compared to traditional technique, right? So in this paper, what they actually developed a simple biosensor, which is made from a gold electrode, over which they coated the polyelectrolyte, and the polyelectrode has been coated with silicon nanoparticles of size 100 nanometers, right? So this is how they developed the biosensors. When we talk about the limit of deduction, right? So consider when a person is having urinary tract infection, which is quite obvious in both male and female, right? So for to identify urinary tract infection, the limit of deduction is, as per the gold standard, that is a culturing technique, is about 10 power 5 colony forming units per ml. This is the minimum limit that is required to identify a person is having urinary tract infection or not, right? Whereas by utilizing these electrochemical sensor, we can able to, so, and one more thing is, whenever there is a urinary tract infection, we usually give culture test, which takes about 48 hours for getting the results. But this simple electrochemical sensor can able to detect the urinary tract infection in less than 15 minutes, that too with lesser limit of detection, right? So as you can clearly see, the E. coli concentration as low as 2 into 10 power 3. Here it is 10 power 5. 2 into 10 power 3 colony forming units per ml is the minimum limit of detection that a person is by utilizing these biosensors, we can able to detect the urinary tract infection. And the next simple physioelectric biosensor has been utilizing quartz crystal microbalance, where the pathogen are being detected, where they have utilized electrode over which the bovine serum albumin has been attached, to which the thiol functionalized antibodies have been attached. And as you already know, this is the functional biological agent. So whenever these quartz crystal microbalance are being oscillating at a frequency based on the applied electric field. So whenever the microbes attaches to these antibodies, there is a change in the mass of the quartz crystal microbalance. As a result, the resonance frequency changes, through which these piezoelectric biosensors are being utilized as pathogen reductions. So the reduction limit was about was improved from 4 log to 1 log colony forming units per ml. So the next is, so till now we have seen what is actually biosensor, what are the different components, what are the different types, and I gave you simple examples of different types of biosensor, one for optical, 2 piezoelectric, and 2 electrochemical, right? So now we'll move on to COVID-19, right? So which we severely face, like in the past 2.5 years, right? So COVID-19 comes under SARS virus, which is severe acute respiratory syndrome virus. Corona, all we call it as SARS-CoV-2. So which is a single strand RNA virus, belongs to beta coronavirus genera in the family Coronaviridae. So when we talk about the diameter of the COVID-2, it is about 60 to 140 nanometers. So COVID-19 was officially announced as a pandemic in by the World Health Organization on 11th March 2020. Like till as on yesterday, there are 64.2 lakh people died due to COVID-19, which clearly, and we all come across the need of diagnosing these COVID-19 in order to make ourselves alive in this universe, right? So it clearly says the urgent need of accurate diagnosis of this COVID-19. So in order to identify how to predict or how to detect COVID-19 in the bodies, we should first know the structural proteins that are present in COVID-19. So when we take SARS-CoV-2, there are 4 structural proteins that is present in the virus. One is the spike, and the next thing is membrane, and we have an envelope, and the nucleocapsid protein. Right. So the S protein is the one which is going to bind with the human cells, and which gains the entry to the host cell. Okay, and the nucleocapsid protein is the viral genome, which is going to be infused to the human cell for the so by which genome the host will be affected by the coronavirus, and it is further spread via sneezing and coughing. So this virus completely, the S, E, and M protein together creates the viral outer protecting membrane. So just give this graph figure will give you an idea about this is the structure of the coronavirus, where this red colors are the spike protein, S protein. Okay, so and these blue color are the membrane proteins in the membrane, and we have an envelope protein. Okay, so on these envelope protein and the membrane protein, we have the nucleocapsid protein, which is the viral RNA. Okay, so this S protein is the one which is going to interact with the human cells. Upon this interaction, it is going to send the information or the confirmation to the viral RNA, the nucleocapsid protein. So once it receives, the viral RNA is being infused to the host cell. Okay, so on the other these are the 4 proteins which are being utilized for deduction. Apart from this, we can also utilize IgM and IgG. IgM are the early response in the body, and IgG are the late response that is being developed in the body. That is the antigen technique. So as already mentioned, the S protein plays a critical role in viral attachment, fusion, entry, and transmission. Again, the S proteins has been further subdivided into S1 subunit and S2 subunit. S1 subunit is responsible for virus receptor binding, and S2 subunit is responsible for virus cell membrane infusion. So S1 again further divided into N-terminal and receptor binding domain. Okay, so as already mentioned, S protein on interaction with the host cell is going to signal to the viral RNA or the nucleocapsid protein. So the nucleocapsid, once it receives the signal, it is going to infuse the RNA, viral RNA to the host cells. So the target for COVID-19 detection can be of 2. We can utilize S protein or viral RNA is used to detect as a target for COVID-19 detection, right? So current testing approaches for COVID-19 is of 2 types. You all come across RT-PCR, right? We also call it as qRT-PCR, that is quantitative reverse transcription polymerase chain reaction, right? So which is the gold standard for detecting COVID-19 as of now, right? So what we all know, we will whenever we go for RT-PCR, swabs from the throat or from the nose is being taken. From the swabs, we will go ahead with PCR technique, which we call it as nucleic acid testing. So the other way is the blood sample will be taken. From the blood, we either use serum or plasma, and that will be used for antibody testing. So there are 2-step testing, nucleic acid testing and antibody testing. So out of these 2, nucleic acid testing is being widely used as a gold standard for the detection of COVID-19. Okay. So in nucleic acid testing, as I already mentioned, we go with PCR, where the swabs from the throat and as well as the nose will be taken. From the swabs, we will separate out the RNA. Viral RNA will be separated, and we will go with PCR. Polymerase chain reaction will be done, and based on the amplification, we will check about the gene sequence with respect to the coronavirus, and based on the results, we will give a positive, whether the patient is positive or negative, right? So in the during the second wave, as RT-PCR is time consuming, we have they have come up with a new technique called RT lamp, that is reverse transcription loop mediated isothermal amplification. So which is an easy technique in which we can able to identify the results within 15 minutes, right? So where this technique doesn't require RNA separation from the swabs, where the swabs can be directly placed in the sensor and which will gives us the results, right? Similarly, the reagents for RT lamps are cheap and they are stable at room temperature. But the only difficulty or the only problem with the RT lamp is it may gives false positive results, right? So that is a problem with RT lamp. But for mass screening, RT lamp is the only choice for us during the second wave. The next thing is antibody testing, as already mentioned. We have in antibody testing where we will be taking the blood samples and the serum or the plasma are being extracted from the blood samples, and it will be tested for IG. We have already seen IgM and IgG antibodies are being tested. The problem with antibody testing is only these IgG are being expressed after 20 days of symptom, right? So that is the only problem with antibody testing. At the time, the patient would be severely affected from COVID-19, right? So that is why antibody testing was quite not rapidly or not being utilized for COVID-19 reduction. So the other sort of reduction techniques that are available is the direct detection of virus, where petri dish cell culture techniques can be utilized. We have seen RNA, that is RT-PCR and PCR technique, and antibody antigen technique also we have seen. The other technique is surface characterization tools, where the virus has to be extracted, and we have to do microscopical studies like AFM, XRD, and electron microscopy, right? Which are quite expensive and time consuming, and the mode of like by undergoing these parameters, the risk of transmission is also high. That is why petri dish cell culture techniques and surface characterization techniques are not being utilized for identifying COVID-19. So as already mentioned, in RT-PCR, where we will be taking the swabs from the patient, nose and throat, and these swabs are being even mixed with the RNA extraction solution, and the RNAs are being extracted and go it with polymerase chain reaction. Once the application has been done, we will check the gene sequence of the COVID-19. So apart from RT-PCR, we also have ELISA technique. We also have lateral flow immunoassay, serum virus neutralization assay, isothermal, so the RT lamp, and CRI, SPR, and next generation sequencing, right? So this table will gives you an idea about the different techniques, their advantages and their limitations. So as already mentioned, culturing techniques, the reduction technique is the sensitivity is about 30 to 50%, and the time duration it takes is about 1 to 3. Slower, so the time it's time, even though it is time consuming, the risk of contamination is high, because the people has to handle those virus physically in hand. Like even though when we use gloves and mask, the risk of transmission will be higher, and when we go with culture techniques, right? And the next thing is next generation sequencing. It takes about 1 to 2 weeks. So even though it is time consuming, we can able to detect the COVID-19 100% when it is muted. Okay. So this next generation sequencing technique is the one which is being utilized. So as we come across different variations in COVID-19, right? Through these past 3 years, we have heard about the different names for a COVID virus. So all these gene mutations that happens to the coronavirus are being identified by next generation sequencing. It is basically utilized for identifying the mutation that happens in the virus, not for the deduction technique. Okay, next generation sequencing is as the time consuming, and it is you identify mutations. And the next thing is immunoassay methods, ELISA method, where the sensitivity is about 2 to 80%. About 2 hours we can identify, where we utilize detect IgG and IgM. As I already mentioned, antibody testing is quite not been utilized because our body develops IgG only after 20 days of symptoms, right? So it is not worthy to detect after 20 days of symptoms, because our body may get affected in a worsen way, right? And the next thing is RT-PCR, which is being widely used, which is of 95%. Within 2 hours, we can able to detect. But as I say, 2 hours, but we have to run n number of samples, and it takes almost 8 to 10 hours to get to run a single set of sample. So it has high sensitive method, requires expensive instrument, long reaction times, right? And the next thing is RT lab, which I already discussed. So we can able to get results within 30 minutes. It is rapid, simple, high specificity, and sensitivity, right? So what the problem here with RT lamp is the false negative results, right? So, and the other thing is difficulty in primer design, false positive results, as I already mentioned. And the next thing is computed tomography, that is CT image, which most of us have been utilized in the second wave. Even though when, as you all know, this coronavirus is going to affect more in the lung area, right? So doctors, whenever the patient is being admitted in hospitals for COVID-19, in the second wave, they are subjected to CT images, because the CT images will directly gives us the amount of infection that happens in the lung area, right? So that we can able to have a rapid results, rapid analysis, and it is not a scientific way to confirm coronavirus. So once the RT-PCR results confirms the patient is being affected with COVID-19, those patients are being suggested by the doctors to take CT in order to know the the percentage of lung infection. That is how CT has been utilized in connection to COVID-19, not to detect COVID-19, right? So when we talk about the nano-enabled smart sensors with respect to COVID-19, right? Researchers have identified optical biosensors, right? So they have utilized molecular beacons, right? So molecular beacons are RNA strands or a DNA strands. So in these molecular beacons, so this is what molecular beacons, right? These molecular beacons are attached with the fluorescent materials. These fluorescent materials are quantum dots, right? So the quantum dots have their own visual color, right? Based on the size, these quantum dots vary based on the material, the size, based on the size, they have their own fluorescence, right? So these molecular beacons, when they are attached, when the RNA, when the strands are attached to together, these molecular the quantum dots, the fluorescent material that are attached to these beacons are quenched, which means there won't be any visible color change. Okay, when these molecular beacons are in closed form, right? So these molecular beacons are attached with the antibodies that are corresponding to coronavirus. Okay, so whenever a sample from the patient has been in or mixed with these molecular beacons, okay, whenever the antigen antibody interaction, whenever the protein, whenever the blood sample contains the antigen of COVID-19, these antigen antibody interacts and these molecular beacons will open up. Okay, so as the molecular beacons open up, these quenched quantum dots or the quenched nanomaterials will show up fluorescence. Okay, so the change in color will give us the patient is affected from COVID-19. Right, so the visual confirmation. So here we don't need any sophisticated instruments, but all these are not being commercialized. All these are research that are ongoing, and as well as the next type of biosensor that are being prepared is microfluidic chips, where the samples that is required for analyzing is very less, where they have taken 1 mule microliters of human plasma that is diluted with 1 ml of buffer solution, where they have utilized gold nano spikes. Okay, so the we have a PDMS, that is polydimethyl siloxane slab, where they have created the microfluidic channel. In the channel, they have created the gold spikes. Okay, and the probes are being attached to inlet and outlet. Okay, so the blood samples, blood plasma has been collected from the SARS patient. This is the gold nanospikes that is being etched in the PDMS mold. Okay, so when these antibodies interact, so as we all know, each and every material have their own surface plasma resonance, which we called LSPR, that is local surface plasma resonance wavelength. Okay, so whenever whenever the plasma has a corresponding SARS-CoV antibody, upon interaction with these gold nanospikes, the surface LSPR changes. The surface plasma resonance is being shifted, which clearly confirms the presence of, or the patient is being affected with COVID-19. Okay, the limit of deduction here is about 0.08 nanogram per ml. So, and the other technique is, it's also visible optical technique using gold nanoparticles that is capped with thiol, right? What we actually do, similar to RT-PCR, the samples are being collected with patients from swabs, nasal swabs or throat swabs. From the swab, the viral RNA has been extracted. Okay, so in the solution, we have the gold nanoparticles that are capped with thiol groups. So upon mixing with these viral RNA, if the viral RNA presence, okay, if the corresponding viral RNA of the COVID-19 is present, these nanoparticles that are functionalized with thiol groups start agglomerating. Okay, so again, once it's agglomerated, which is the time taken to this process is about 5 minutes, upon which we add RNAs, so which will cleave the RNA that is attached to these agglomerated nanoparticles. So once the RNAs are cleaved, these nanoparticles again start aggregating and get deposited. So by which we can clearly see these nanoparticles are getting precipitated. So there is a phase separation. Okay, whenever there is a phase separation, so this naked eye deduction, which clearly confirms the patient is COVID positive. Okay, this is one way of utilizing nano-enabled smart sensors as well as nanoparticles for COVID-19 detection. So this technique only takes about 10 to 15 minutes, and the limit of deduction is about 1.18 nanograms per ml. So, and it is a visual naked eye deduction, which doesn't require any sophisticated instrumentation techniques. So these are some of the, this table will give you some of the FDA approved biosensors for COVID-19 detection. The manufacturer, the first one is Abbott, in which they target nucleocapsids. Specificity is of 99.9, sensitivity is 100%. Then is Access Bio, where they target spikes and nucleocapsids. Specificity 98.9 and 98.4. And Beijing Wanti Biological Pharma, where they concentrate the target protein is spike, right? So, and BioEd Healthcare, where the target protein is nucleocapsids. So, like this, each and every company have their own molecule and the specificity and sensitivity. So, the challenges with biosensors, there are 3 prominent challenges that we see in biosensors. One is, as I already mentioned, the biosensor, the unlight and the biological element is going to interact, and which is going to change a physiochemical change is going to happen. Okay, so the magnitude of the change that happens between the analyte and the biological sensing element is very low. Okay, capturing those changes is a pretty big task. Okay, so this problem is being overcome by the utilization of nanomaterials as well as other biomolecules. We can able to improve the capture of these low magnitude signals. And the next challenge is scale up of this method. Okay, so whenever we develop a biosensor in a laboratory environment, which will give us better results. But when we actually go with the real sample evaluation, it will give us different. So scaling these biosensors from lab to product is another one challenge. And the third challenge is the limit of detection is very important. So the minimum amount of analyte that our biosensor can detect is also important parameters. So basically, the limit of detection is quite less in case of magnetic and plasmonic biosensors compared to electrochemical biosensors. But these plasmonic and magnetic biosensors, plasmonic and magnetic techniques require sophisticated instruments compared to electrochemical device. So that's it. Shall we move on to question and answer, the next session?
Okay, sir.
Participants, if you have any queries with respect to the two sessions, you can ask me.
Excuse me, sir. One small info. Sorry to interrupt.
Yes, ma'am.
Participants. Dear participant, one small info. Now we are posting the Google form. Kindly fill the Google form. It will be considered as your attendance for the today's session. The link will be active for next 15 minutes. Please fill the Google form. This link will be considered as your attendance for this today's session. So please fill the Google form. We are posting in the chat box. Priya ma'am, please post the link, ma'am.
Okay, ma'am.
The link is posted. Please fill the link. The link will be active for next 15 minutes. It will be considered as your attendance. Thank you, everyone.
Participants, please ask your doubts. Sir, I am having a few doubts.
Yes, ma'am.
For that, the soya product is very good for healing the wounds, you said, no?
Yes, ma'am.
In that PEO, you said, no? That what is meant by that PEO?
Actually, PEO is polyethylene oxide. It's a polymer. Actually, soya protein isolate. So we have taken the soya protein isolate from the soya bean, and when we try to convert that natural polymer into fiber, it has not been converting because of its globular structure. So even when we apply higher potential, it has not been converted to fibers.
For blending, you use that PEO, whether it will not affect the burns to the worst condition.
Actually, PEO is a FDA approved polymer which can be utilized for biological activity. So the main use of PEO is to convert. It's actually a good fiber forming polymer. So since soya protein can't be converted into fibers, we mixed blended PEO and soya protein so that soya protein isolate has been converted to fibers by the help of PEO.
It will not affect the burns, sir. It is a good.
Yes, ma'am. It is a FDA approved polymer. It doesn't affect the skin burn. It's any wound. It doesn't cause any adverse action as well.
Okay, sir. And another doubt I'm having that in dye filtration, the titanic dioxide is sensitive to ultraviolet rays, visible rays.
Yes, ma'am. Yes, ma'am.
For that, you prepared lycopene.
Yes.
Like, if it is exposed to UV, what is the disadvantage, sir?
It is not the disadvantage. So, actually, TaO2 is a UV visible. It's a UV activated photocatalyst, right? So, if you want to utilize TaO2, you should have a UV source to activate it so that it acts on the dye. Our motto is to reutilize these TaO2, also convert this TaO2. We don't need any UV source to activate. For example, sunlight can itself can activate this TaO2, so that we prepare lycopene, which absorbs the visible light and donate the electron to the TaO2 to activate it, the TaO2. That is what the basic motto, ma'am.
Okay. And then the byproducts of phenyl naphthalene and the phenol, isn't it?
Yes, ma'am. Yes, ma'am. So those are the byproducts of the Congo red. Congo red dye has been converted to biphenol, phenol, and naphthalene.
So how you will remove this phenyl naphthalene and phenol?
Ma'am, those are colorless compounds, ma'am. Actually, these waters actually now the textile industries are going to or moving towards zero water discharge. So that once the dye has been degraded, the water will become again normal color. So they will be utilizing those water again back with the next sort of dye and reutilize those water. So these waters are not being consumed back by humans as a drinking water. So that is why we don't care about naphthalene, phenol, and other sort of byproducts.
Okay, sir. And if the person is affected by COVID virus, it can be found by this S protein and viral RNA.
Yes, ma'am.
How long it will take to test this S protein and viral RNA? After how many days we can detect this RNA in the human body?
Ma'am, the S protein is the one which is going to interact with the human cell, which is not going to be in the body. So the viral RNA is the one which is going to be injected into the body, which is again going to host, which is going to get replicated in the human body, right? Okay. So we can able to detect within 5 days of the infusion.
Okay. Okay, sir. Thank you.
Okay. Any other doubts?
Anisha, somebody raised the hand. Nisha?
No, ma'am. Till now, no one. Anyone? Please raise your hands to any queries. Means, please.
Please unmute the participants.
Participants, if you have any queries, means please raise your hands. We are unmute your mic and then please carry on your questions.
If your mic is not working, you can also type in the chat box so that I can reply you.
I think one participant, Nagesh Rao, raised the hand. Sir, any doubts? Participants, you can ask your doubts.
If there is no question, then shall we wind up?
Wind up, sir? Okay, sir.
Yeah, well, I just want to conclude, ma'am. One minute.
Okay. Okay, sir.
Okay, so if you have any queries, you can contact me through my mail ID. Right. I also want to acknowledge my students. Without them, we can't do any research sort of activities. So all these accomplishments are being for my students. I also want to thank my collaborators, my guide, all of them. So I also like to thank the organizing committee for inviting me for this ATAL FDP. I hope I would have given some knowledge to you. Feel free to ask me any questions through this mail ID. Thank you for the organizing team for inviting me.
Thank you, sir. Nisha, conclude.
Thank you.
Ma'am, shall we go for the formal vote of thanks?
Okay, Nisha.
Yeah, ma'am. Good evening, sir. On the behalf of Siddharth Institute of Engineering and Technology and ATAL FTP IoT-driven resource devices for healthcare and defense application, my deepest gratitude to you, sir, for giving this time, valuable time for us. And first of all, we thank you. We know about the biosensors and nanotechnologies and all, but you give you the great draft about this, and then you motivate us to learn and research about more things about the biosensors. Nowadays the pregnancy kits and then the COVID kit and this and all the main booming of our world. So thank you, sir, to make us to make more research about this. And then thank you so much for your time, and we are hoping in future also your collaboration we needed. Thank you so much, sir.
Thank you.
Thank you, sir.
Thank you, ma'am.
Wonderful presentation, sir.
Thank you, ma'am.
We gained, we know a lot of information from your presentation. Thank you, sir.
Thank you. Thank you. Thank you.
Thanks for your time. Nisha, ask participants to fill the Google form.
Hello. Hello. Good evening, madam.
Good evening.
Yes, sir, you can proceed, sir. Nageswar Rao.
Nisha,
Tell me, sir.
Hello. Good evening, sir.
Yes, sir. Yes, sir.
Sir, actually, I tried to interact with the sir session chair, but unfortunately, you have disabled the mute, and I could not able to unmute myself, and even I could not able to post any message in the chat also, because you have disabled the chat also, sir. So for that reason, I raised my hand, and later I lowered my hand.
Okay.
In the subsequent time, my mobile restarted.
Okay, sir. It's not an issue, sir. If you have any queries, please send a message. Okay, sir.
Sir. Thank you.
Thank you, sir.
Rahul, unmute the participants chat box.
Now everything
Enable the chat box.
Yeah. Wait, ma'am. I will.
Enabled, ma'am. Enabled.
Yeah. During query sessions, we have to enable. Yeah. Okay.
Rahul, don't disable the link. It should be up to 9:30.
Okay.
Rahul?
Okay, ma'am. Yeah.